We wrote a Lagrangian for bosons with a chemical potential because we're interested in a system of particles with a finite number of particles. And that induced a spontaneous symmetry breaking, which therefore led to this Lagrangian as a function of the Goldstone mode, which is rolling along the gutter, and the Higgs mode, which is climbing up the wall. So now our goal is to focus on the low energy part, which is associated with the Goldstone mode because it is massless. And to do that, we will quantize this theory using many path formulation, and we will integrate out the Higgs field. Once we integrate out the Higgs field, we will end up with an effective Lagrangian which only depends on the Goldstone mode. We can already isolate the term in the Lagrangian which doesn't depend on the Higgs field. And to integrate out the Higgs field, we need to rewrite the path integral in terms of a Gaussian path integral. This implies an expression for A and for J. We can then solve our Gaussian path integral. The propagator D is the inverse of A. We are interested in the low energy behavior, and in particular for cold atoms, the kinetic energy is very small. The interaction will always be here, but the kinetic energy can be turned off. Therefore, we are going to neglect this term. Subbing the expression for the propagator into the expression for W, and also using the expression for J, we then get our path integral as function of theta only. This gives our expression for the effective Lagrangian. As expected, we see that there is no mass term for the Goldstone mode. This effective Lagrangian characterizes the physics of our superfluid at very low energy. So our next task will be to extract the dispersion relation from this Lagrangian, and from this we will be able to interpret some spectacular behavior of superfluid at extremely low energy.